So in this lecture, we are just going to discuss about the training and runtime complexity of our SVM. That's algorithm we are discussed in previous lectures. I think till now the algorithms all of you are clear. So let's see how the training time complexity and runtime complexity. So if we just consider the training time complexity, first we consider the training time complexity. If we just see, we can training this SVM in two ways. So you can use to stochastic gradient descent, and or you can use specialized dual algorithm that we see in the that we'll see in previous classes. They are in to train model. We are using here the specialized algorithm that is called that is coming from our dual equations. Okay. But it is coming from dual equations. Okay. And subsequently I think in recently this algorithm is developed, and this algorithm is called the sequential minimal optimization problem, or another language. If you search in Google SMO SVM, then you can find it. So in specialized algorithm we can using in dual problem, and after some modifications the mathematicians are coming into the sequential minimal optimization problem. Or in another language we call this algorithm as SMO algorithm. Okay. Mm, so simple. If you are interested to learn about this algorithm, just simple Google it on Google it SMO SPM. Simple Google it, then you can find the details. There are many research paper and Wikipedia article also available on Google. Just if you are interested, then you can learn from it. Okay, I'm not going to discuss that. So these algorithms are there have some development, some modifications of the dual problem. Then they are arise the SMO algorithms. Okay, and this also is very useful in SBM. After developing these SMO algorithms, the some training time complexity they are reduced. Okay. So just if you know the Python language, so there we can learn the sklearn library. They have one very important library that we call the sklearn library. Okay, in sklearn library. So in sklearn library, they have inbuilt one model SVM. So if you are interested, but in sklearn they have not available any SMO SVM. But if you are interested to find the SMO, so so simply they have one library in Pythons that call the leap SVM. In Python they have one inbuilt library. Just if you are interested, just type in on leap SVM Python. Just simply you can find it easy. So it is the best libraries for using simply. So this library is designed for mainly using the SVM, only for SVM. But in sklearn there are many kind of regression techniques, classification techniques, and many more. But this library is specially used for SVM only. Best libraries for training SVMs. Okay, this is the best one for SVM only. It is only this library is only built for SVM, to training the SVM model. Okay, so if I am not wrong, sklearn internally uses leap SVM also. Also, scanner is internally also uses leaf SVM. If I am not wrong, if I am not wrong, okay. So simple. If you see the training time complexity of SVM, training time complexity, if you just see the training time complexity of SVM, it is near about approximately, it is near about order of n square. Okay, simply it is near about order of n square. Or simple, this is for only for kernel SVM. This library, this time complexity is only for kernel SVM. Okay, and it will be polynomial, it will be RBF, it will be any kind of, it is the it is approximate time complexity for any kernel SVM. Okay, so in 19, I think in about 2007, approximately 2007, there come one research paper. They are just modified this complexity by simply they are some modification they are applied in this algorithm, and they are proved that so they can reduce the training time complexity in order of nd square. Okay, if d is less than n. Well, they are some simple reduced from here to here, this algorithm. Okay, I think in approximately 2000, yeah, near about 2000. I'm not properly remember what is approximate time, but it is near about 2007. So it is the more optimized algorithm for me. It is the more optimized algorithm from kernel SVM. It is the more better algorithm from this. Okay, this one is the more better one. Just if you're interested, just search it on Google. You can easily find it. I'm not coming to the details of this research paper. Okay, so if you just see, so it is totally impossible to training our data in, if you are if you just consider a internet company, then the number of data sets in the number of data in training point is so large. So if the data is number of data is large, so order of n square is so much. So it is for a low latency model, it is impossible to training our model. So it is impossible to use this use this time complexities model. So if our n is large, so in such cases order of n square, it's so large, it is impossible. So large order of n square. Typically, just if you see n is so large, typically you will see in a internet company. Yeah, in internet company, typically we see this in internet company, where we need a low latency model. So this is impossible, because typically in such kind of situations we typically don't use this. Not use SVM when n is large. Okay, we don't use this kind of. So this is our simple runtime complexity order of n square. So because of high runtime, sorry, this is our training time complexity order of n square. So because of high training time complexity in low latency model, this SVM is not generally used. So let's see what is the training time complexity. Let's see what is the runtime. This is our training time complexity. Now let's see what is the runtime complexity of SVM. Let's see the runtime complexity. So if you just see our query functions, just remember our query function. So I'm writing it. where I is equals to, sorry, 1 to n, and alpha I yi k of xi xq plus p. Okay, so this is our simply query functions. By simply applying these functions, we can find our output of a query point. Simple, we can see also previous lecture, we will see this kind of thing. So here simple alpha is for what? Here we are simple alpha is equals to 0. We see that for alpha is equals to 0 for our non-support vectors, and alpha greater than 0 for support vectors only. We have see this thing end of things. Okay, so just to see that it is not, if you just consider non-support vector, it is not depend, this function is not dependent on non-support vector. This function is only dependent on support vectors only for support vectors this function is responsible. Okay, so the runtime complexity for this algorithm, if you just see the runtime complexity for this algorithm is near about support vectors, number of support vectors. If our number of support vectors is let's say our number of support vectors for this algorithm is k. So in this case, this order of complexity for this algorithm is order of kd. Okay, k is our number of support vectors, and d is our number of dimensions of our data sets. Okay, k is our number of data sets, k is k is the dimensions of our data sets. So in general, if you see in general, if number of support vectors, it is typically happen the number of support vectors is less than number of non-support vectors, it is typically we see. So if number of support vectors is small, it's small. Okay, if our number of support vectors is small, then what the number will be 0 to n. So k would be like on 0 to 1 for any number, it k would be here. So if it is small, then this model is better. So then we can easily build a low latency runtime model, low latency model by simply using runtime complexity. If our support vectors is small. So but in general, if you see, we have to consider the worst case always. So just see, just here see, k would be anything, it is lies on k 1 to n. So if suppose if in worst case k is very large, that is equals to n, so in such scenario this model is not workable, it is not perfect, because here runtime is increased. So in such cases, the runtime is increased. Okay. Suppose let's take for a company, for a internet company, our n is suppose let's take 100,000. So okay, so reports and k is 10,000. K is 10,000. K means what? K means number of support vectors. K is 10,000. Then in such cases, it is okay if our dimension is small, so small. If d is not a large number, then this thing is okay. Then we have no problem. But if we have k is approximate equal to, if k is approximate equal to n, and for we see for a text data set dimension d is also large. We see this kind of thing in text data set. For a text data, we see this kind of things occur. So in such situations, this kind of algorithm is not workable, this kind SVM would fail. but there have some modifications. Just in previous lecture we call the string SVM, so we can easily add, but it is not a good as good as others ones. Okay, but we can you can, if you interested, you can easily use it. And one thing, just if you just compare this runtime complexity model with logistic, just remember the logistic regression model. Just remember the logistic regressions model. So in the logistic regressions model, the runtime complexity, just remember runtime complexity for logistic is a simple order of D. Simple order of D. So the kernel SVM is not as good as logistic regression. Okay, but why it is not good? For runtime purpose, our logistic regressions model is good, because simple its runtime complexity is as much low. Because this one is low, KD, simple k is greater than 1, always k is greater than 1, and k is lies in this number. So simple, this one will be always better, and this thing for SPM. This thing order of D is always better than order of KD. So for runtime purpose, the logistic regressions always on for from SVM. So always logistic regression is better for runtime purpose. Okay, I think you see the differences between logistic regressions and SVM runtime complexities. What is who are on in such situations, and in which situations it is applicable to which more applicable, and in which situations which model we can easily use. Just see, you can see these kind of things, and also you see the training time complexity. And so also, just before going finish this lecture, I'm also going to remember, so also there have two hyper parameters. If you just consider the soft simple, if you just consider the soft margin SPM, if you just consider this SVM, so here we see that here we have two parameters, C and sigma. C is for what? C is for our soft margin, and sigma is for what? Sigma is for RPF. We see that, and we have choose these parameters by simply using, there are various type, random grid search, random search, and also there are many techniques. We see these kind of things, and also in the next of this part of the next lectures, we will see how to choose the best parameter, and we will discuss the real world cases, how to handle the various kind of data set, and where it is usable. Just in this lecture we will see that training and runtime complexity, and we compare this with logistic regression. Okay,